Alright, so in this video what we're going to look at is how we use U-substitution with definite integrals, so when they have a boundary. So here's an example. So the U-substitution part is going to be the same. What you're going to have to worry about is these boundaries that are in terms of x. So let's say we're looking between 0 to 1 of the function x times the quantity x squared plus 1 to the third dx. So when I look at that, I'm looking at a function that looks like this, and I only put from 0 to 1. So I'm looking at this piece here, and this area, this really kind of area that would be here, is what I'm looking to find. And I don't know how to integrate that, so I could use a U substitution. So in this, I would let U equal x squared plus 1, because that's what's inside. So the derivative of u with respect to x would just give you 2x times that dx. And I only have x here, so I could say that I have du over 2 equals x dx. So I would have u to the third times du over 2. So I substituted. That was my u sub. Now here's where it's a little bit different. So here, these boundaries right here are in terms of x, but my function now is in terms of u. So I need to plug this b and a values into what u equals to get them in terms of u. So I start with a. If I put 0 in here, 0 squared plus 1 is 1, and 1 squared plus 1 is 2. So I'm going to evaluate the integral of 1/2, I'm going to move that 2 out front there, that 1/2, from 1 to 2 of u cubed du. So not only did I change the function, I had to change the boundaries. So if I go back to Desmos, what I'm saying is this little piece of this cubic function right here, so if I drew this in here, that has the same area as this piece right here from 0 to 1. And they do have the same area. So they're completely different functions, but under this red curve and under this blue curve we'll have the same area. And that's basically what we did. Now we just have to find that area. So let's find the area. I'm going to go back to my function. The antiderivative of u cubed would be u to the fourth over 4. And I'm going to multiply that by 1/2. And after I multiply it by 1/2, then I have to evaluate it from 2 to 1, or you can multiply afterwards, however you want. I would probably just write it as u to the fourth over 8, evaluated from 2 to 1. And if I do all that, so you'd put in 2 there, you'd get 16, what would you get? 16, so that's 2 minus 1/8. So that would give you 15/8 is your area. So no matter which curve I looked at, whether it was the red curve or the blue curve, the area underneath is 15/8. So it's pretty easy. I mean, it's basically the same thing. Let's try another example here. If I want to evaluate from -1 to 0 of x times the square root of 1 minus x squared dx. Again, this is a pretty complicated function, but I can get it back down to its parent function. So u would be 1 minus x squared. Du is going to be negative 2x multiplied by dx, because the derivative with respect to x. So du over negative 2 is equal to x dx. So if I substitute, I can get the square root of u du, and out front I'm going to have negative 1/2. I'm just going to do that in one step. And now you need to change your boundaries, because these are in terms of x. This is like x equals 0 and x equals -1, but we want them in terms of u. So if you put in -1 here, you're going to get 0, because you would have 1 minus -1 squared. And then if I put in 0, I'm going to get positive 1. So negative 1/2 is the multiplier. The antiderivative of that would be u to the 3/2 times 2/3. And I'm going to simplify this. These 2's can cancel, so I get negative u to the 3/2 over 3. And I'm going to evaluate that from 1 to 0. And so I'm going to get negative 1/3 minus 0, which is just negative 1/3. So remember, these two functions look totally different. If you graph them on Desmos, they're going to be two different functions that you're looking at, two different curves, but the area underneath these two, so the area of this function from negative 1 to 0 is negative 1/3. The area of this function times negative 1/2 from 0 to 1 is also negative 1/3. Okay? And we're going to try one more with the special U-sub. Hold on one sec. Okay, so we're going to look at one that's one of those special U-substitutions, like you have to do double substitution. So we're going to look at the definite integral from 5 to 1 of the function x over the square root of 2x minus 1 dx. So these are one of those special ones that we worked on last week. So when I do this, my u substitution, my u is going to be 2x minus 1. My du is going to be 2 dx, which I don't have a 2 coefficient up here, so I know that it's going to be du over 2 equals dx. So I'm going to have a 1/2. I know that I'm going to have the square root of u in the denominator. And I know that dx is just going to be du over 2, which I already put over here. But then I still have this x right here. So we need to go back and do that back substitution. Hold on. So I need to replace this x. Well, I know that u is 2x minus 1. So that means if I do some algebra, u plus 1 divided by 2 is equal to x. So I'm going to put this in for x right here. So I have 1/2 times the integral of u plus 1 over 2 square root of u. So this is u plus 1 over 2 du. I can actually move this 2 out front as well, so I'm going to make that 1/4 times the integral of u over the square root of u plus 1 over the square root of u du. So I'm breaking it up into 2 parts. So that's 1/4 integral. That would be u to the 1/2 plus u to the negative 1/2 du. And we have to go back up because I wrote too big. Now we need to change our boundaries. So our boundaries were 5 and 1. But remember, we need to put them in terms of u. So if you put 5 in here, you get 2 times 5, which is 10, minus 1 is 9. So that upper boundary is 9. And then if I put 1 in there, 2 times 1 minus 1 is 1. So my lower boundary is 1. And I'm going to go down here and fill it in with all this algebra we did. So this is 1 to 9. So now I take the antiderivative, so I'm going to have 1/4. This would be 2u to the 3/2 over 3 for the antiderivative, plus 2u to the 1/2 from 9 to 1. So I'm going to have 1/4. I'm going to leave it there for now. I'm going to put in 9. So 9 to the 3/2, so that's the square root of 9 is 3, cubed is 27, times 2 is 54, over 3, which is 18, plus square root of 9 is 3, times 2 is 6, So this piece gives me 24. And then I have to subtract, so I'm going to subtract this whole next part where I put in 1, which is going to be 2/3 plus 2. I'm sorry, my handwriting is really horrible today. So 1/4, 2/3 plus 2 gives me 8/3, so I have 24 minus 8/3. And when I do that, I'm going to have, well, you can do that a couple different ways. I could take 1/4 of each of them, so that's 6 minus 1/4 of 8 is 2/3. Yeah, 2/3. And 6 minus 2/3 would be 5 1/3. Now you obviously can use your calculator. I made that a little bit harder because I didn't have my calculator. And just so you know, for definite integrals, this is a special U-sub with definite integrals. This is probably one of the hardest problems you'll have to look at, but I would expect at least one of those on the test. So what you're going to do now, just go back to Canvas, look to see what the assignment is from the book. I want you to use your class time as much as you can. Try to answer all those definite integral U-substitution problems. And have a good day.